Okay, this is the follow-up notes to what we started in class today, section 3.5, graphing with transformations of functions, even and odd functions. I'm going to do a separate video for even and odd functions since that's not on the exam, and I will title it even and odd functions just so you know that's what it is, because we want to focus mainly on what do you need to know for Thursday's class. So we'll come back to the even and odd in the separate video. And right now we want to look at transformations of functions. We started talking about this in class, and we're just going to go through the different types of transformations again. And as I go through and work the problems, I'm going to do each one kind of as, here's how you would do it with a transformation, and then the next one that's kind of similar I will do using just a table of values. That way, in case you're not as comfortable with the transformations, you can see how these would be worked out just using an XY chart. And then there's some problems where we will describe transformations just by looking at an equation. And then the final piece, which is piecewise functions. I will cover them in this video, but I will also pick one or two for us to do in class before we review on Thursday. So there are vertical shifts. This is when you have a function that has a parent function, which we talked about the 5 parent functions you guys need to have memorized. We have a parent function, and then at the end of that you have something either added or subtracted on after that. So a plus c or a minus c at the end. If you have a plus c, your y values are getting bigger, so your whole graph just shifts up that amount. If you have a minus c after the end of a function, you would be subtracting or losing height, so you'd be going down. Horizontal shifts are a little bit different. You have something that happens inside the function. That means before they square root or before they square or before you take an absolute value. If there's something subtracted or added inside of a function, it's going to move the graph either left or right a certain amount of distance. So the thing is, it's always when anything happens inside. So if something happens inside a function, you do opposite to what you see. So for example, if I have like f of x minus 3, because I see a minus 3, I intuitively want to say left 3. That's kind of how our brain wants to process that. But it's inside the function part, so it's going to be opposite of what we see. So it moves to the right. If it's a plus inside, it's going to move to the left that amount. So the whole shape will shift either right or left depending on if it's plus or minus inside the function. The vertical stretches and compressions are if you have a number in front, so something like 2 times f of x, or a half times f of x. If the number in front is bigger than 1, you're stretching vertically by that factor. So notice how this is stretching by c amount. So if this was a 2, this would be 2 times c. So it's getting x. It's getting multiple bigger of that. And if it's between 0 and 1, so in other words like a half or a third or 3/4, it actually shrinks it or compresses it vertically. Now, same could be said for can you stretch horizontally or compress horizontally, and that is true as well, except when the number inside the function, notice this time it's inside not outside, is bigger than 1, you're actually going to compress. You're going to get skinnier on the x-axis. And so that's skinnier horizontally if you want to think of it that way. And if the number inside is 1/2 or 1/3, we're going to actually get wider. We're going to get bigger. We're going to stretch out horizontally on the x-axis. So notice this is opposite to what you think. A big number actually makes you squeeze in tighter, and a small number makes you stretch out wide. So again, if something happens inside of a function, f of x, if it's inside that parentheses, it's the opposite of what you think. Whereas if it happens outside, you do exactly what you see. And then the last type is the reflections. If you have a negative in front of a function, so this is 2 to the x, and then they made it negative 2 to the x, that flips your whole picture across the x-axis, so upside down. If your negative happens inside the function, notice this time it's in the exponent of that, then it flips horizontally across the y-axis. So you can think of this as being like a negative f of x whereas this is f of negative x. That's the difference between those two reflections. So we say that this is a reflect over the x-axis, and this one is a reflect over the y-axis. Okay, so you put all of these transformations together. You had pretty much 4 different types: the vertical shifts, horizontal shifts. I guess it's really 3 types: your stretches and compressions, whether they're vertical or horizontal, and then your reflections. So then we get into, what are we trying to transform? Well, there's 5 parent functions that we're going to deal with. There's obviously a lot more functions out there. These are just the 5 that we deal with in this section. So there's the square function, which is f of x equals x squared. Notice it's just a parabola. They didn't magically make up any of those ordered pairs. Someone came along and just did a table of values and did -2, -1, 0, 1, and 2. You square each of those things and you get the points that are plotted here. So that's what x squared with nothing added or subtracted or multiplied looks like. It's centered at the origin right there for its vertex, and it has that nice symmetry. X cubed would be our next one. Notice when you cube something, it stays positive if it was positive, but if it was a negative number, it's going to be negative. So you kind of get this parabola that has a split personality, up and down. Notice it's still centered at 0 because 0 cubed is 0. And you do need to know the general shape of these so that if you see a cube in a formula for a function, you know that it should have this general shape if that's the only variable that we have to that power. Square root of x, we talked about this one in class today. The reason you can't do a negative when you plug it into this table is because, remember, our our radicals that are even have to have a domain that is greater than or equal to 0. So we picked 0, 1, and 4 because those are all perfect squares. So that's how you get these points. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. Cubed root of x, you can plug in negatives because we can take a cubed root of a negative number. So notice this looks sort of like the x cubed, but it's kind of been turned on its side as well. And then the final one was the absolute value of x, which is a V shape, because any negative you plug in reports as a positive as well. So an example that we're going to do together for this video, we're going to be looking at different types of transformations. We're going to describe it, and then we're going to graph it. And so I'm going to switch it up. So every other transformation, I'll do either it by the transformation method, or the next example that's very similar, I will do just using a table of values, so you can see that you can use either method for graphing these. So we're going to sketch all of these, and then we're going to describe what transformation happened. The most important thing you want to look for is what is the parent function here. I always write that over to the side. See, I see the squared part. So that means this is related to the parent x squared. And I do a little doodle off to the side to help me kind of visualize what x squared looked like, so I know what I should expect, similarly, my new one to look like. And remember, if you don't know these points off the top of your head, you use a table of values to find them. Okay, so there's what x squared looks like. There's a +3 at the end. Anytime something happens after the part that's been squared or cubed is already done, it's going to be a vertical shift. Vertical shifts, you do exactly what the sign tells you. So this is going to be moved up 3. So each of these points is going to be shifted up 3. So 0, 0 was the original center, so that's going to go up 1, 2, 3. We had 1, 1. That was another point on x squared, just using a table of values to find that. And if I go to 1, 1 and then go up 1, 2, 3, and then there was 2, 2 squared is 4, so if I'm at 2, 4, and then I need to go up 1, 2, 3. So notice that's that side of that parabola. And because parabolas have symmetry, there's going to be matching points. That's what it says, make use of symmetry if you can. So since I know the shape, I know it's going to have this match here. So the description is that the function shifted up 3. Okay, so that's just how you would do it using the transformation. For the next one, I know I'm still going to have to know kind of what shape to expect so that I know if I got it right or not. But I'm actually going to show you this one by a table of values just so you can see that if you don't have all of the transformations 100%, you can still graph these. So if you're doing a table of values, as long as you're not dealing with the square root of x, you can pretty much plug in any x's you want, but there's a really good way to know where to start the middle of your table. Whatever makes the inside part of your part, so if it's the cubed part or if it's, you know, an absolute value, whatever makes that set equal to 0, which in this case would just be 0, that's going to be the center of your table. So we actually are going to center our table at 0. That's going to help us always make sure we get enough points to graph it. So I'm going to pick some things smaller and some things bigger and just show you that I could still do this graph with a table of values and not worry about trying to describe the transformation right away. So I put in -2, that would be 2 minus 1, so that's going to be a 1. Put in -1, that would be a 1 minus a 1, which is 0. Put in 0, absolute value of 0 is 0, so that's just going to be -1. And then absolute value of 1 minus 1 is going to be a 0 again, and absolute value of 2 minus 1 is going to be a 1 again. So notice I have 5 points. I'm going to plot those. And you're going to see the V shape comes out using the table as well because I was very careful about where to center my table. I'll show you one in a minute where you actually do have to center it off of 0 because something else is inside. So -1, 0, 0, -1, and then 1, 0, and 2, 1. Very much similar to a parabola except it's much sharper and it's a V shape. Now, if I didn't know the transformation off the top of my head, I could be able to pick it from the picture because I remembered that the V shape was centered at 0, 0. So this has been shifted down 1 because of the -1 at the end. So I did the same thing up here. I just didn't have to do all the work with the table because I knew the parent shape and I knew what the transformation was. All right, so let's look at one that has a horizontal shift. So we have this x minus 2 to the third. I'm going to do this one using transformations, and then I'll do the one after it using a table so you can see that I can still do them either way. When you're talking about to the third power, the parent is x cubed. And again, you don't have to have the table memorized or the picture memorized, but you can do a table of values to find what the picture looks like. I always recommend 5 points if you're not sure what the picture looks like. So -2 cubed is -8, -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. So 0, 0, 1, 1, -1, -1, and then we have these points that are way down here. For 2, 8, and 2, -2, -8. So notice it has this kind of shape we talked about, the parabola that's kind of split in opposite directions. Okay, so when something happens inside of a parentheses before it got cubed or squared, that means it's going to be a horizontal shift. That means we're moving either right or left. And you always do the opposite of what you see when you have something inside the parentheses. So even though this is a -2, I'm actually going to move right 2. So if we look at this, 0, 0 needs to move right 2. I'm just going to use the main 3 points in the middle and just make sure I have my shape correct. -1, -1 needs to go right 2. +1, that's this point right here, needs to go right 2. And then just make sure you draw the generic shape of an x cubed. So that has been shifted to the right 2. And that is the x cubed shape. Okay, so this next one I'm going to do using a table. It's the cubed root of x, but this is what I meant by you have to sometimes be careful and not just always start with 0 as the center of your table. You'll get kind of a skewed result sometimes. So anytime you're trying to use a table, you always want to take whatever's inside here, set that equal to 0, and then this is going to be the center of your table. So that's going to be -1, and we pick 2 things smaller and 2 things larger. And then we just plug them in, and we can even get decimal approximations if we want, but hopefully we'll find some nice points. So the cubed root of -2 plus 1. So see, that's not such a nice point. Well, yeah, it is. Actually, it'll be okay. This is cubed root of -1. So cubed root of -1 is -1. I think it's the next one that's not so nice. Oh, nope, sorry, I did not write that correct. I wrote the -2 in. I was skipping ahead. Okay, so cubed root of -3 plus 1. That gives you -2, which is not a nice number. So I was correct when I said that the first time. So we can take our calculator if we want. We just need to get a rough estimate of what that is. So I'm going to type in 2 negative, because I have to do things backwards on this calculator. And I want a cubed root, which I am not sure where that is. There it is. So it looks like that's -1.3. I'm going to double check that. That doesn't look right. So let's do cubed root of -2. 0.577. So let's double check that. So 0.577 times itself 3 times, because sometimes this calculator is not the best because you have to enter things backwards. That is not the right way for that either. Sorry, give me just a second. This is just a funny calculator. So I think I have to do parentheses. So cubed root of -2. Let's see if that works. No. Let's try -2. So see, your calculator might be easier than this one. And let's try the cubed root this way. Oh, nope. I guess I could raise it to the 1/3 power. That would be quicker. So -2 raised to the 1/3 power. Divided by 3. And that is negative, yeah, so the first time was correct. So -1.3. Sorry about that. So -1.3. Okay, the next one will come out nicer. So this is -2 plus 1, which is cubed root of -1, which is -1. And then we get the cubed root of -1 plus 1, which is the cubed root of 0, which is just going to be 0. And then cubed root of 0 plus 1 is cubed root of +1, which is +1. And then we get cubed root of 1 plus 1, which is cubed root of 2, which is going to be +1.3. Okay, so we're going to plot these. So -3, -1.3, -2, -1, -1, 0, 0, 1, and 1, 1.3. So notice this is still the cubed root shape, which remember, cubed root of x looks like the guy above that we did this x cubed, but it's on its side, kind of like this, like a snake. So for this guy right here, notice that it has been shifted to the left 1 instead of being centered at 0, 0, which makes sense with that transformation. We do the opposite of what we see. So instead of plussing 1, we're really taking it to the left 1. So again, you can either do this by knowing the parent shape and just transforming those points using the transformation, or you can do a table of values. So let's talk about E. E has the negative square root of x. So when we have a negative in front, it's going to be a reflection across the x-axis, but we do need to know our shape. So our parent is just square root of x, and that has the points 0, 0, 1, 1, and 4, 2. And remember, I don't know those always off the top of my head. Sometimes I have to do the chart, but you do have to keep your chart in a domain that makes sense, so no imaginary numbers. So 0, 1, and 4 are all perfect squares that are easy to plug in. Okay, so that's my parent. So that's the generic shape that I'm building off of. A negative in front means to reflect over the x-axis. So we take each point and we flip it upside down across the x-axis. 0, 0, though, is already on the x-axis, so it can't flip. 1, 1 would become 1, -1. 4, 2 would become 4, -2. So if you have a negative out front, the graph just flips across this x-axis. It flips upside down. And there are my points. This one has a negative inside. Instead of doing this one using a table, I'm just going to go ahead and do the reflection again. It's just as easy to do it either way, but, well, no, I can do a table. It's not a big deal. Still going to be square root of x, so it still has that shape that we were just looking at. If you want to do a table here, you do need to set that inside greater than or equal to 0 to figure out what you're going to start your table at. And it is important to notice that if you're going to use the table version instead of doing this by shifting or flipping, if you have a negative inside of a radical in front of x, you have to divide that over, and it's going to change the direction that you actually pick your x's. Since this is a negative, we're going to pick negatives so that they turn into positives when you multiply. So we're going to start our table with 0, and then I'm going to pick -1 and -4 because they're perfect squares and the negatives will cancel each other out. So this is square root of -0, which is just square root of 0, which is 0. This is square root of -1, which is square root of 1. And square root of -4, which is square root of 4. And that is 2. So notice if there's a negative inside, we reflect across the y-axis. And we're showing that to you using a table, or you can memorize that that's what the transformation is. Okay, so notice it flips this way. Okay, for g, we are looking at a parent of x cubed. Notice there's a cubed there. So x cubed was this guy. It was like a parabola that was split in half up, half down. If you cube 1, you get 1. If you cube -1, you get -1. If you cube 0, you get 0. So that's 3 points that I usually use when I transform this. If you have a number in front of your function, notice it's not being cubed. It's not in a parentheses. That is going to be what we call either a vertical stretch or a vertical compression. If this number is greater than 1, it's going to be a stretch. Okay, so it's not in the cubed part, it's not being cubed, it's just times it out front. It's greater than 1, so it's going to be a stretch. What that means is you're going to double your y values. Okay, so all of my y values are going to get doubled. So that means it's going to be 1, 2. I'm just doubling these right here, so times each of these by 2, just the y values. 0, 0 would still be 0, 0, and -1, -2. So this would be 1, 2, 0, 0, -1, -2. It's the same shape, it's just a little bit thinner than the original one. It's been stretched vertically. How you would write this so that if you had to write a description is you would say the function has been stretched in the y direction, since it happened outside of the x cubed, by a factor of 2. Okay? Honestly, when it comes to stretches and compressions, I'm more likely to tell students to do everything by a table and then to describe what they see. And that's just because sometimes it's hard for students to know when is it happening to X and when is it happening to Y. Anything that's outside of what's going on is going to happen to Y. If it's inside, like this 2 is inside that parentheses, it's going to happen or affect X. And it's not going to double it. When it's inside, remember, it's going to do the opposite of what you think. So we'll get to that one in a minute, but let's look at this one. We're going to do this one with the table. Since there's nothing really inside here happening with X, it's all happening outside, I would just stick with -2, -1, 0, 1, and 2. You shouldn't have to adjust the table unless there's something adjusted on the X part, like a plus or a minus something. So then if I plug these in, this is 1/4 times -2 squared, which would be 1/4 of 4. So that's just going to be 1. 1/4 of -1 squared would just be 1/4 of 1, so that's a fourth. 1/4 of 0 squared is going to be 0. 1/4 of 1 squared is going to be a fourth again. And 1/4 of 2 squared is 1/4 of 4, which is 1. So just working each of those out individually to get the table. Then we plot our points, so -2, 1, -1, 1/4, 0, 0, 1 1/4, and 2, 1. So it does have the parabola shape because it's an x squared. Okay, so that's why it has the U shape. But notice this has been compressed. So this one was a compression by a factor of 1/4 in the y direction. So same thing. Anytime it happens outside of the function parent, it's a y direction change. Okay, so that leads us into I, which is something happening inside the parentheses. When it happens inside, it's going to be the opposite, and it's going to affect x. So this is really going to be a 1/2 effect on x. Okay, you always do the opposite when it's inside. So if we want to do this using the transformations only, you have to know your parent, which is x cubed, since we have a cube there. Remember, x cubed has this shape. -1, -1, 0, 0, and 1, 1. And this says we're going to take half of all of those x points. So half of 1 is a half of 0 is still 0, half of -1 is -1/2. Notice nothing happened to the y values when it's inside here, okay, before being cubed. And notice that the way I'm doing this is you figure out what the effect is, and when it's inside, it's opposite, so it's reciprocal, and you just multiply that by each of those x values. So this would be 1/2 1, which is right here, and then 0, 0, and then -1/2 -1. So notice that is the x cubed shape, but it has been, what we call this is a, excuse me, this is a compression on the x. The x direction by 1/2, okay? And then our last one of that type, I'm going to do this one by a table. This is going to be square root of x, so you do need to know your general shape. And then we're going to do a table of values for this one. Notice this is also inside, and it looks like it's supposed to be a compression because it's a 1/9, but remember we're going to end up doing 9/1 effect on x. So it's actually going to stretch if you were doing a transformation in the x direction. Okay, so I need to make sure I keep within my domain, so 1/9 x needs to be greater than or equal to 0. Anytime you're doing the square root one, you need to make sure you set this up. So if I multiply 9 over, it's still going to be 0. So our table's still going to start at 0. I'm going to pick things that make perfect squares. If I plug in 1, that'll be a perfect square over a perfect square. I could also plug in 9 because 1 and 9th and 9 would make 1, and that probably should be enough. So you could plug in as many points as you want. You could have plugged in points that were closer together between 1 and 9. You would just get decimals. So this would be 1/9 times 0, which is square root of 0, and that's 0. 1/9 times 1, which would be square root of 1/9, and that would be a 1 and a 3 if we take the square root of both top and bottom. And 1/9 times 9 is square root of 1, which is 1. So 0, 0, 1, 1/3, so that's really tiny, and then 9, 1. So notice this has been stretched way out horizontally instead of being like this. Okay, so that was what we did in this first A through J, is that we went through and did every type of transformation singularly by itself. So we did vertical shifts, we did horizontal shifts, we did reflections both ways, we did stretches and compressions vertically and horizontally, and I never did any combinations of more than one transformation at the same time. I also showed you how to do them just by looking at the parent and doing the transformation from the points, and also from just plugging in a table of values, but knowing a little bit about how the picture should look so that you know you've got enough points. For K, we're combining two transformations at the same time, and we did L in class, so I'm not going to do that one again, but for K, we're trying to do, it looks like a vertical shift and a horizontal shift at the same time. So you could do this one by a table, and I'll show you that as well for the same problem, but I'm going to show you how I would do it with a transformation. The first thing I locate is the generic feature that makes me know what shape I'm looking at. So because I see a squared, I know that I'm probably looking at this parabola shape right here. Parabola is centered at 0, 0 when it's got this, and it has a 1 squared is 1, and negative 1 squared is also positive 1. So those are 3 key points for that. This tells me that there's a vertical shift up 1 because it's happening after the squaring. Inside, I also have a -3. You always do opposite of what you see when it's inside. So instead of left 3 because of the negative, we're actually going to go right 3. So I should be able to graph this right now just by knowing the two transformations. I will point out that when you're doing transformations, you always work from the one that's closest to x out, just like order of operations. So we are going to go right 3 first because that is closest to x, and then we're going to go up 2. So that's the order that we are going to transform. If someone asks you to describe the transformation, you also describe it in that order. You would say the function has been moved right 3 and then up 1. All right, so if we go from 0, 0, I always like to start with my center vertex point. I would go right 1, 2, 3, and then up 1. So that gives me this new point. 1, 1 is another point that we had on the original, so I'm going to go right 1, 2, 3, and up 1. And then negative 1, 1 is right 1, 2, 3, up 1. So there's my picture. If I wasn't comfortable with transformations, I could also do a table to confirm this, or I could have done it by the table anyways and then describe the transformation. The key thing with doing a table is you want to focus on what's in the parentheses here and make sure the center of your table makes that 0. So I'm going to start with a 3 in the center of my table because that would make x minus 3 equals 0. And then you pick 2 things smaller and 2 things larger. When you plug those in, let's see, 1, I'm not going to work through these on showing all my work, but 1 minus 3 is negative 2. Negative 2 squared is 4. 4 plus 1 is 5. 2 minus 3 is negative 1. Negative 1 squared is 1 plus 1 is 2. Notice that's this point right here, so that's matching up. 3 minus 3 is 0. 0 squared is 0 plus 1 is 1. There's that point, 3, 1. 4 minus 3 is 1. 1 squared is 1 plus 1 is 2. That's matching with that point. And then 5 minus 3 is 2. 2 squared is 4 plus 1 is 5. And you know, mine are a little off, but they're pretty close because I drew this by hand. But those middle 3 points matched up exactly. And we are just sketching, so you're just trying to get it in the right location and the right general shape. Okay, so we did L in class. So this next part right here is having you not graph anything, but just explain the transformation in words. And when you do this, you want to make sure you always go in the order of closest to x and then work your way out. So for this one right here, notice that there is going to be a shift right 1 because of that minus 1 inside the f of x part. And then because there's a 3 in front, there's going to be a stretch or a compression to y. When it's bigger than 1, it's going to be a stretch. So a stretch by a factor of 3 in the y direction. Anything that happens outside of that f of x is happening to y. Okay, so we would want to write that as a sentence. So this is the function has been, and to make sure you write the correct one first, this is closest to x, the minus 1, so this would be first, and this would be second. And that does matter for partial credit. So the function has been shifted right 1, then stretched by a factor of 3 in the y direction. Sorry for my chicken scratch. Okay, so let's look at the next one. There's a plus 4 inside, which means we're going to do the opposite of what we see there since it's inside, so that's going to be left 4. And then there's this negative out front, which is going to be a reflection over the x-axis. Give my computer just a second to catch up. So reflect x-axis. I'll write that out a little bit better over here. Ooh, part of my equation went away. That is interesting. So that was a blocks for some reason. Okay. Hang on just a second. Let me see if I can get that to fix. All right, and I got it fixed. So that negative in front was a reflect over the x-axis. So if we were going to write this out, the +4 is actually closer to the x, so that's going to go first. The reflection is going to go second. And if you're graphing this, that is also the order that you graph it in. So if you're trying to do the transformations, you always work from the inside part out. So then this would be the function, we're just going to say f of x, was shifted left 4 and then reflected over the x-axis. Okay, and then the final one is there's a 1/2 inside. So when something happens inside, it's actually opposite to what you see. So that's going to be a 2/1 on x. So that essentially means it's a stretch in the x direction. And then this is at the end, so it's a -3 at the end, so that's going to be down 3. This would be closer to x, and then the vertical shift would be second. So we're going to f of x is stretched in the x direction by a factor of 2, since that was the reciprocal of that, then shifted down 3. Okay. All right, the final piece of problems, and like I said, I'm going to do both of these on this video, but then I'm also going to pick one to do in class or maybe 2 on Thursday just to make sure you're good. Piecewise functions are not difficult, but they are just an application of a table of value. So essentially what someone has done is they've given you a function and they've given you just small domains for each piece. There are 3 rows on this function right here. When there's 3 rows, there's going to be 3 separate tables that we're doing. So each of these lines is going to be a table. So -2x is going to have an XY chart. And you could do these by transformations, but I find students usually mess that up and it's a little more difficult for them. Tables of values are a little bit more comfortable for everyone. So this says for this first table, x has to be less than -1. You do always start with that endpoint, but you will indicate whether or not the endpoint is opened or closed. So -1 is the starting point, even though it doesn't say equal to, so we indicate that that's going to be open. Then we pick values less than -1, so -2, -3, something smaller. You plug those in. -2 times -1 is 2. -2 times -2 is +4. -2 times -3 is +6. And this would continue on because this says for any x is less than -1. So we're going to graph just this piece. So this is -1, 2, and that's an open circle since that's our starting point and it was not equal to. The rest of these will just be regular points. So -2, 4, oops, sorry, not high enough, and -3, 6. Let me erase that 1 point. And of course, it's not letting me erase it. I'll have to redo it. There we go. So notice this is a line. So it's just going in a straight line forever in that direction because all of these x's are less than 1, so the pattern's just going to continue. X squared happens between -1 and 1, so we need to have all the points between -1 and 1, which is -1, 0, and 1. They're both going to be open on the endpoints because there's no equal to. But 0 is going to be just a regular point. So you don't put open circles in the middle of a graph. It's only going to be on the end of the points where the domains stop and start. And then -1 squared is 1, 0 squared is 0, 1 squared is 1. So negative 1, 1, open circle, 0, 0, 1, 1. So this is part of a parabola. And mine shouldn't be that close. My open circles are a little exaggerated so that you can see them. So there's that first one. There we go, a little bit better. Okay, this third table is for when x is greater than or equal to 1. So 1 is the starting point, and it's going to be closed this time because it has the equal to. And this says greater than 1, so we're going to just pick numbers greater than 1. This has no x to plug into, so that means no matter what you see, the answer is always negative 2. So this is what we call a constant function. It's just going to be flat. So 1, negative 2, and that's closed. 2, negative 2, 3, negative 2. It's going to continue that way forever since it says it's always going to be negative 2 anytime x is greater than or equal to 1. So you have three different chunks, a slanted line, a part of a parabola, and a constant flat line. So let's do one more of these. So this one is just another variation. We have 3 different rows again, so 3 different parts. X minus 3 when x is less than or equal to negative 2. Negative x squared if x is between negative 2 and 1. And negative x plus 4 if x is greater than or equal to 1. So negative 2 and then everything less than, so negative 3, negative 4, and this one is going to start with negative 2 being closed because of the equal to. So negative 2 minus 3 is negative 5. Negative 3 minus 3 is negative 6. Negative 4 minus 3, plugging it into the equation, is negative 7. So negative 2, negative 5 with a closed circle. Negative 3, negative 6. Negative 4, negative 7, and this is continuing in that pattern using that same slope essentially. Okay, so this guy right here is negative x squared for negative 2 to 1. So just to be safe, let's do all the values between negative 2 and positive 1. And it's open on both of your endpoints. So your endpoints are the numbers at the beginning and end because there's no equal to. So be careful here. This is negative negative 2 squared. So that's negative 4 because you square it and it becomes positive, but then there's a negative in front. Negative negative 1 squared is going to be a 1, but then you put a negative on it. 0 squared times negative 1 is just 0, and then negative 1 squared is 1 squared is 1, and then there's a negative. So this is going to be an upside down parabola, it looks like. So negative 2, negative 4 is open. Negative 1, negative 1, 0, 0, and then 1, negative 1 is the other endpoint, and it is also open. So we get a part of a parabola there in the middle. That doesn't always have to be a parabola, it just was for these two examples. It could have easily have been an x cubed in the middle. So you just have to plug in and see what the table gives you. So greater than or equal to 1 with this having a closed endpoint because of the equal to, and we just need a few values. So this is negative 1 plus 4, so that would be 3. Negative, and then 2 plus 4, so that would be 2. And negative 3 plus 4 is 1. So 1, 3, and that's closed. 2, 2, 3, 1. And this is continuing in this fashion forever. So there's my piecewise function. So this one had a positive slope because it was 1 over 1. This is an upside down parabola, and then a negative slope right here. You do not graph anything that is outside of the boundaries for each piece. So notice that these are just pieces of parabolas and pieces of lines. That is why they are called piecewise functions. And that is the end of the 3.5 video. We'll probably spend a good deal of our time on the review questions, I'm guessing, on some of these Chapter 3 topics. I'll bring in another piecewise function or two to try together in class, plus some more transformations just to get us started and make sure that we're good with those. And I will see everybody on Thursday.